Well, thank you very much, Mason, and good afternoon, ladies and gentlemen. It's a pleasure and honor to be here. And David stole my thunder about, I was going to also have an elaborate praise for the organizers of this meeting. It's been an excellent meeting. So with that, I'll move on and save my time for other things. I want to apologize for the talk. The title of the talk, by the way, Future Directions of Risk Analysis, is pretty broad and ambitious title. And the title came about because Professor Moslem and I were talking, and he said, well, what's the title going to be? And I said, well, it's a placeholder, use Future Directions of Risk Analysis. And, but I should have qualified it, but time ran out. But it's in regard to peer, in regard to natural hazards, in regard to, so I want to qualify it way down. Okay, now, yesterday, Professor Mitrani-Risey talked about the history and how we got to certain locations. So the past is prologue for the future. And I would have liked to, with more time, explain, if we're going to talk about the future of risk analysis, how we got here. But I will simply cite a paper, a 76-page paper I have from a few years ago about the history of it. And for the students in the audience, I think actually you might want to read this. It's kind of interesting. I hope you would find it of interest. And it's available on a website I'll give you at the end also. So the outline of my talk is basically the risk criteria, risk equity, and risk governance. But first, before I get to that, I want to talk about earthquake early warning, the excellent presentation that was given yesterday by Richard Allen. And we have a slide here, let's see if this will that? Yes. Video here. This is from from March 2011, and the sound's not coming through, I'm sorry, but it is, what's happening is, this is a meeting at the Architectural Institute of Japan. These are the leading structural engineers in Japan. You may have glimpsed Professor Steve Mayen there a moment ago. And we had just received over the annunciator a warning, earthquake early warning, that an earthquake would come in about 5 to 10 seconds. And you observe all of these people, and now you're starting to see the Klieg lights moving and so on. And you'll still observe the Klieg lights are moving, the people are not moving. Except me, by the way. I jumped up and ran to the door. Because I was sitting underneath those Klieg lights next to Steve Mayen. So I'll stop it right here. It goes on for a little longer. But, and see, because I can play it later perhaps with the sound. But now, let me ask you a question. And I'm going to ask for a show of hands here. Given 5 seconds like that, what would you do? 1001, 1002, 1003, 1004, 1005. Okay, all of you who would duck and cover, raise your hand. All of you who would run for a door, raise your hand. All of you who would evacuate the building, raise your hand. Okay, so you're about split 50-50, by the way. Like the people there, the leading structural engineers in Japan and some of the leading structural engineers of America, they didn't know what to do. And I would say, since you were split 50-50, you don't know what to do either. So effective warning consists of an alert, which thanks to MyShake we have now, the detection, analysis, and decision-making for that alert, the transmission of that alert to the recipient, to the audience, the receipt if you have a smartphone now, and then after that comes the audience, us. And you have to comprehend the message, and then you have to take action, the payoff. If you don't take action, the rest of it is a waste of time. So we have to know what to do ahead of time, because the 5 to 10 seconds may not be enough. And it also depends, of course, where we are. So we need tailored messages and planned actions. The planned actions are what to do. It depends who you are, a child, a teacher, able-bodied person, where you are, home, school, gasworks, what kind of a building you're in, and which is largely an engineering domain. The answers to these questions, I think, largely come out of the engineering domain. Tailoring the message so that people comprehend it. In other words, the engineers figure out, perhaps, engineers and perhaps others, perhaps the the public health and medical professions can figure out what to do. But to get that tailored message is determined, I think, largely comes out of the social sciences. And that message differs whether you're in the lounge of a hospital or the operating room, whether you're in the gym, the classroom, or the chemical laboratory of a school. So, therefore, if we're going to have effective earthquake early warning, we need for every building an assessment of performance of that building, both the structural and non-structural components. We need for every room in that building the assessment of the performance of the ceilings, the furniture, the fixtures, and so on. And then a decision as to what is the best option for different kinds of people to drop, cover, and hold, to remain, to flee, how to flee, where the refuge areas are, and so on and so forth. And we need to communicate that. And that communication can be by placards. We could just have a sign on the wall in the event of an earthquake. And when you go in the room, it's there. It could be through enunciators. It can be through the smartphone someday, when we are assured that the phone will sense where you are, that will sense that you're in this room and not up in the Ida Spruill room up on the second floor. And then therefore the message will be tailored for you. So all of these things are needed for earthquake early warning. And these things are not going to come from the seismologists. They're going to come from you. So I just wanted to mention that to you. Now, moving on. I want to talk about risk criteria. Yesterday, Ron Klemenchik showed this table, and it comes out of ASCE 7. And I've taken risk category 3, and I've highlighted something that probably applies to a fairly large fraction of our buildings. Probability of failure annual probability of failure of a component in a building is the requirement, in effect, is 2 times 10 to the minus 6th. If the building has a 50-year life, which is what's referenced there, then we get 10 to the minus 4th. So if we have a big building with 10,000 components, we might have one failure of a component during its life. And a component would be a beam, a connection, perhaps a column. That may or may not be acceptable, but that doesn't sound too bad. Once during 50 years, we'll have one structural problem in a building. Many of us have seen much more than that, of course. When we go, however, and those are for different load combinations. So we have load combinations for the basic loads, for snow and ice, for earthquake, and those are all sort of independent. They're not in any way treated. The probability of failure applies to each of those load combinations. There's no combination of those load combinations. And also the next table for earthquake cites, for example, a probability of 5% given the MCE, maximum considered earthquake, for a building, 5% probability of a structural system stability failure. Now, I don't quite understand that number. If that means that given an MCE, we have a 5% failure of the building, the structural system, then in San Francisco, where we have 200,000 buildings, are we going to have 10,000 buildings failing? That would seem to be the interpretation of that. We're talking about risk criteria here. So, and these are new buildings, not the existing buildings, which presumably are not even built to the ASCE 7 standard. And that 5%, where does it come from? So when people are going to ask, what's my risk? What are we going to tell them? Well, the snow and ice, the wind, the flood, the earthquake are all siloed. Those load combinations are all separate. They don't want to know what their ice risk is or their earthquake risk or their flood risk. They want to know is, what's the total risk? What is my risk? It's a summation of these if we treat them independently. Nowhere in the code is that there. We really, unless you do a special study, really don't have an answer for this question. And that is one of the most basic questions that any reasonable person would be asking us. And by the way, ASCE 7 doesn't even treat fire. That's NFPA. And now the decision making, if they know their risk, is hardly democratic. This 5%, where did it come from? Well, it's the public delegates our decision making to trained, trusted professionals, the engineers and the building officials, us. And okay, well then they're in good hands, right? I think they are. But then it's modified at the city council level by special interests, developers, usually modified downward, developers, realtors, owners. And the actual risk, as I've just discussed, is not largely known. So, and it has not been deliberately chosen. That 5%, I think it traces back to the ASCE Lateral Forces Committee of 1953 in their report, and some people sitting in a smoke-filled room near the corner of Market and Sansom. And some of us know probably who those people. Just saying, pulling that number out of the air and saying it sounds good. I think that's where it really traces back to. So it hasn't been really deliberately chosen. There have been examinations. Ellwood and Cornell in 1980 looked at it. There have been more recent efforts to look at it. But whether it's the right number or not, hard to say. Also, the risk is very heterogeneously born. Brian Strong yesterday, Chief Risk Officer for San Francisco, pointed that out, the vulnerable populations and so on. I will come back to that point. With regard to, by the way, it has not been deliberately chosen. I just want to mention a paper by my colleague Keith Porter. It's in Earthquake Spectra recently on the public's role in seismic design provisions. He's been working with, his co-author is a moral philosopher, a professor in the Department of Philosophy. He's a moral philosopher who examines these kinds of questions. And I think Porter is really trying to push the envelope on this and try and direct us in a direction where these things are more democratically chosen. So what is needed? Professor Saidi said, let's discuss the what, and then somebody else will deal with the how. So what is needed? More transparent, rational, open risk communication and decision-making process. We don't have it. Okay. And by the way, the 50-year life, I just want to mention that. In San Francisco, this is a histogram of the age of the buildings, and the average age, median or mean, is 1932. That means the average building in San Francisco is 88 years old and aging. Last year it was 87, now it's 88 years old. And it's actually probably going to age for quite a bit longer. Actually, many buildings in our cities are well over 100 years old. So this 50-year life is just, the actual risk is probably double, or maybe perhaps triple. And by the way, I wanted to ask for another show of hands. How many people in this room live in a building that was built before 1975? Raise your hand, please. I'd say 2/3 of the people in this building, in this room, raised their hands. Before 1975 is basically before modern seismic design. The 73 code is really, at least I consider, the first modern seismic code in terms of loading post San Fernando. And it's also 45 years ago, so it's about that 50-year window. So we're all living beyond our risk tolerance there. So now with regard to risk equity, this is a map of, forget which one, I guess this is you guys can read it at the top there. That's the earthquake shaking, okay? And you can read them all at the top there. It's hurricanes, winter storm events, tornadoes, floods, wildfire. Varies widely across the country. And detail, as Brian Strong showed us yesterday, this is simply the liquefaction potential, but it varies within detail within any location and by the population also. So I'm coming to this question of heterogeneously born. By the way, with regard to that, a little plug here. We had this study for FEMA, National Institute of Building Sciences, where we developed these that show that mitigation is cost beneficial, and this is some of the maps of to what degree is it cost beneficial in different parts of the country. That was for earthquake, this is for wildfire, and we have it for flood and other things too. Okay, so that's one kind of risk. Wildfire. We've all seen the wildfires that we've had in the last couple of years here. The 44 people killed, $85 billion in 2017 due to wildfires. I think most of you are familiar. We have debris flows, geotechnical issues. 2018, the Camp Fire, and same sort of thing. Very rapid spread of fire within a few minutes. The air pollution we all experienced went across the country. So 2 years to wildfires, 170 dead, $115 billion in losses. What are we doing about this? What are we doing about this? The Oroville Dam, 188,000 people evacuated. Refineries. We have all these refineries in the Bay Area. Pipelines in LA, that's not a highway map, that's a map of gas and oil transmission lines. This is the Kinder Morgan pipelines in the Bay Area carrying jet fuel and so on. And we have the San Bruno gas explosion. This is the crude by rail. It's, because of the Bakken fields in North Dakota, transportation has to be by rail. It's coming across these trestles, including this over 100-year-old trestle in Martinez. These rail cars derail, kill a lot of people. There's been a number of these accidents across the country. We haven't had one in the Bay Area. We've been lucky. And lastly, this thing about cordoning off, so that one high-rise building here, the risk that it represents is, in the event that it has damage and is cordoned off, is shared by its neighboring buildings. So, with regard to risk, this is a target-rich environment we live in. And with regard to the disaster life cycle, the disaster life cycle can apply to any of these things, to flooding, to dam failure, to earthquakes, to fires, to refineries, any of these things. So, it's a target-rich environment in which all the peer skill sets, hazard analysis, modeling, decision-making, communication, they similarly apply to all the other hazards. I learned this when I started working, after working for years in earthquake, I started working in flood. It's a one-to-one mapping. Everything we do applies equally to flood or to avalanche risk or to actually terrorism risk. Any of these, the same model applies to all. So therefore, I personally think that PEER ought to be the Earthquake Engineering and Extreme Events Research Center. And if somebody says, well, which is it? Is it earthquake engineering or extreme events? The answer is yes. And if they persist, you say, listen, let's worry about the risk and get on with that. So, risk is a byproduct of most activities. Why engage in those activities? Well, they're necessary and profitable. We have to do it. Who reaps the profit and who bears the risk? Well, refineries, profit goes to the investors, risk goes to the neighbors, crude by rail, profit goes to the companies and the investors, the risk goes to those who close to the right-of-way, the neighbors. So what is needed? More equitable sharing of risk. This is difficult because risk is often, typically, location-specific, and the investors in Chevron will not move to Richmond. And anyway, should the risk be shared or should it be reduced? So reducing it now, how do we go about reducing it? And I want to give you an example from Fukushima. Fukushima, we all know, 6 boiling water reactors. One of them, or 2 of them, are heavily damaged. Approximate cost, it occurred in 2011. The approximate cost is $1 trillion. This is the first $1 trillion natural hazards, or at least what they call NATTEC, natural and technological hazard event. This number, most people peg this event at $300 billion, but the cleanup is costing $700 billion for Fukushima. And the citation is at the bottom there. So if we take those 6 boiling water reactors for their 40-year, give them a 40-year life, 1,000 megawatts each, 70% availability, they would have generated over the 40 years about 1.5 trillion kilowatt hours. And they cost $1 trillion. The damage was $1 trillion. So we divide one by the other, we get 68 cents a kilowatt hour. This was the cost of the risk. And it was not included in the electric bill. So the electric, I looked at my bill yesterday, I'm paying 22 cents a kilowatt hour. That's if the externality, the risk, is ignored. So a fundamental what is the price of risk should be included in the costs of goods and services. It's not. It hasn't been for many reasons, difficulty of quantifying it. But now all the tools we've seen, we have a solid basis for quantifying it. So as we heard yesterday, cash is king, so let's price the risk. The analog, we have a pricing of carbon tax now. So let's have a risk tax. It promotes risk reduction by producers, and it provides funds for risk reduction. So with regard, so that's one way to start reducing the risk, is have a risk tax. That will make people sit up and pay notice. Another way, by the way, we have the analog of the LEED building certification for green buildings. It's worked very well, it's been very popular. U.S. Resilience Council, kudos to Evan Rice and the people there, Ron Mays. They have a similar placarding system. I don't think it has the same penetration. Personally, I would make the placards a lot simpler, tag buildings. If you went around and started tagging buildings like this, it would get people's notice. So, This is almost one of my last slides. Something completely different. I'm an advisor to the World Bank. I do a lot of work overseas for them in a lot of countries. This was just one of the national strategies we developed, in this case Morocco. And basically what it amounted to was we developed a hazards-like program, however, which is all geo-noded together. So all the ministries both contribute the data, so it's always fresh, and use the data. And you can see that we had what we call National Office of Risk Management, a norm to set the risk norms for the country. And that norm is supported technically by a Center of Risk Excellence, CORE. And I would like to see PEER become the core for risk management in the United States or Western United States, whatever. This structure would, at least for the state of California, fifth largest economy, and I can go into more about how CORE interacts with all the people on this diagram. But this is the kind of thing that we're doing in other countries, and we ought to be doing it here. So the future of risk analysis, in conclusion, earthquake early warning creates a need for ubiquitous structural and non-structural seismic assessment. This will have to be addressed in a semi-automated manner. We've seen the tools that are coming out of this. I mean, the structure for motion that's able to transfer a couple of photographs into a structural model. I mean, we can actually start doing this. And the high-performance computing and everything else, the tools we got here, we can do it. The seismic risk doesn't exist in a vacuum. I think PEER should be really addressing seismic risk within a multi-hazard framework. And actually, since everything maps one-to-one, and particularly like risk communication, I mean, there's really not that much difference between communicating the risk of an earthquake and the risk of a wildfire at a certain level. I would like to see that. Risk is unfairly borne currently. Okay, life is unfair, but we should strive to make it fairer. Risk reduction requires risk governance, and money talks, so a risk tax is a viable vehicle for risk reduction. And by the way, some of these things are in the special issue of the National Academy magazine that Tom O'Rourke edited and very kindly invited me and Keith Porter to contribute to. So some of these things are written there and spelled out in a little bit more detail. And I want to thank Tom for inviting us to contribute to that. Now, last question. Professor Saidi said, well, let's, the what, and the how will come later. So how are we going to get all those done? Well, you're going to do it. We got a lot of bright students here and a couple of bright professors. So I think, next generation. These are some of the things that I think you ought to be thinking about and working towards. And with that, I'll just simply say thank you very much.